The distinctively fluted surface and elongated hills in this view are caused by wind erosion of a soft, fine-grained rock, called yardongs. These features are aligned with the prevailing wind direction. This wind direction would have dominated for a very long time to carve these large-scale features into the exposed rock seen today. Yardongs not only reveal the strength and direction of historic winds, but also reveal something of the host rock itself. Close inspection by HiRISE shows an absence of boulders or rubble, especially along steep yardong cliffs and buttresses. The absence of rubble and the scale of the yardongs tells us that the host rock consists only of weakly cemented fine granules in tens of meters or more thick deposits. Such deposits could have come from extended settling of volcanic ash, atmospheric dust, or accumulations of wind-deposited fine sands. After a time, these deposits became cemented and cohesive, illustrated by the high standing relief and exposed cliffs. Curiosity rover recently collected a rock sample on Mars and analyzed the sample by dropping the pulverized rock into instruments within the rover's body. One of those instruments, called CHEMIN for chemistry and mineralogy, used X-ray diffraction to discover the presence of an iron carbonate mineral called siderite in samples from 3 different locations, regions enriched with salty minerals called sulfates. The discovery of siderite may help solve one of Mars' mysteries. There is strong evidence that liquid water coursed over the planet's surface billions of years ago, suggesting Mars had a thick, carbon-rich atmosphere rather than the wispy one it has today. A thicker carbon dioxide atmosphere is required to provide enough pressure and warmth for water to remain liquid on a planet's surface. Otherwise, it rapidly vaporizes or freezes, which is the case on Mars today. That carbon dioxide and water should have reacted with Martian rocks to create carbonate minerals. However, when scientists study the planet with satellites, that ample carbonate hasn't been apparent, even at Curiosity's site. It's possible that other minerals may be masking carbonate from satellite near-infrared analysis, particularly in sulfate-rich areas. If other such layers across Mars also contain hidden carbonates, the amount of stored carbon dioxide would be part of that needed in the ancient atmosphere to create conditions warm enough to support liquid water. The rest could be hidden in other deposits or have been lost to space over time. Billions of years ago, a river once flowed across this scene in Morth Vallis on Mars. Like on Earth, these riverbeds can get filled up with rocks that are cemented together. After Mars became a colder, drier place and the river disappeared, the rocky river bed remained. In this view, we see a dark ridge snaking across the surface. The dark ridge is the old riverbed. It is raised above its surroundings now because these softer surroundings have been eroded away, whereas the rocky riverbed resists that. Scientists call these ridges inverted channels, and many of them are visible in this area of Mars. While sunrise and sunset on Mars resembles an earthly sunset, closer inspection reveals alien oddities. A day on Mars lasts 24 hours and 39 minutes, so sunrise and sunset follow nearly the same rhythm as they do on Earth. But sunsets and sunrises offer a different palette of colors than they would on Earth. For starters, the sun only radiates the equivalent of a partly cloudy afternoon's worth of light. That's because Mars' average distance from the sun is 141.6 million miles. This increased distance reduces the intensity of sunlight. Not only that, But the solar disk shrinks from the familiar 0.5 degrees across we see from Earth to 0.35 degrees at Mars. Here on Earth, your little finger extended at arm's length would cover the equivalent of 2 suns, but on Mars it would be 3. Dust and other fine particles in the atmosphere scatter the blues and greens from the setting or rising sun to color it yellow, orange, and red. When these tints are reflected off clouds, sunset colors are amplified and spread about the sky. But things are a little different on Mars. The ever-present fine dust in the Martian atmosphere absorbs blue light and scatters the warmer colors, coloring the sky a familiar ruddy hue. At the same time, dust particles in the sun's direction scatter blue light forward to create a cool blue aureole near the setting sun. If you were standing on Mars, you'd only notice the blue glow when the sun was near the horizon, the time when its light passes through the greatest depth of atmosphere and dust. On Earth, blue light from the sun is scattered by air molecules and spreads around the sky to create a blue canopy. Mars has less than 1% of Earth's atmosphere, so we only notice the blue when looking through the greatest thickness of the Martian air and dust around the time of sunset and sunrise. When the sun sets or rises on Earth, it's squashed like a melon due to atmospheric refraction. Much thicker air adjacent to the horizon bends the sun's light upward, pushing the bottom of the solar disk into the top half, which is less affected by refraction because it's slightly higher. Once the sun rises high enough, we're looking at it through less atmosphere, refraction diminishes, and it becomes a circle again. On Mars, however, the sun's shape doesn't change. At least it's not noticeable to the casual eye. This is because the air is too thin for refraction to make much of a difference. Twilights linger longer on the red planet as well, because dust lofted high into the stratosphere by storms continues to reflect the sun's light for 2 hours or more after sundown.